It's my pleasure to introduce Ed Neal. I know Ed as a fisherman who hails from the Olympic Peninsula where I come from, but I don't think he's going to tell us about fishing today. Instead, he's going to tell us about his work at the USGS. Ed holds degrees in environmental science from Washington State and a graduate degree from the University of Otago in New Zealand. But since 1995, he's lived not in Washington, but here in Juneau, and he works on water quality, fluvial geomorphology, and hydroclimatology. And as the title of his talk suggests, he'll be talking about the impact of climate change on stream runoff, and what that might mean for hydro, I think, is a question we'll want to ask. So please join me in welcoming Ed Neal.
I guess I should get this loaded. There we go. I'm going to talk primarily about, that's not showing up on the screen, is it? Okay, I'll trust you. I'm going to talk primarily about some of the climate model projections that are pertinent to stream flow in Southeast Alaska, and discuss how changes in climate might influence runoff patterns and annual runoff. And I'm also going to discuss some of the data that we've seen from the few long-term gauges that the USGS operates in Southeast Alaska. Okay, in general, the climate models indicate increases in annual precipitations in the higher and mid latitudes like Southeast Alaska. There's a fair amount of uncertainty in the magnitude of these these increases, and some of the models predict much larger increases than others. One of the things that's less uncertain is that increasing temperatures might result in smaller proportion of precipitation falling as snow, especially in areas of marginal snow cover. And that's particularly pertinent here in Southeast Alaska. In fact, in large parts of Eastern Europe and European Russia, Central Canada, California, some of these shifts in stream flow from springtime to winter have already occurred as the climate has warmed and the winter precipitation tends to fall as snow, or as rain rather than snow. Changes in the glaciated basins are a little bit more complex, but most of the models project that glacier recession will initially lead to additional runoff to that produced if the glacier was in a steady state. However, the sustained deglaciation will eventually result in reduced runoff if the glacier decreases significantly in mass. Rather than relying solely on the model projections, we can draw some inferences to the potential changes in runoff based on environmental data. A study we completed in 2002 examined differences in stream flow between the two most recent modes of the Pacific Decadal Oscillation. And results of this study will provide some clues as to what we might expect under warmer climate conditions. In 1976, the North Pacific region, including Southeast Alaska, experienced a pretty dramatic shift in climate conditions. It saw large increases in winter temperatures and some smaller increases in summer and autumn temperatures. And rather than a gradual change in climate, this change is better represented as a step change that occurred in the winter of 1976 and 1977. This is illustrated with this image of trends in the mean annual departure from average temperature. Now, if we look at it from 1951 to 2001, we see an indicated trend, an increasing trend in temperature. But if we look at it from 1977 to 2001, there's no significant trend in temperature. And if we look at it from 1951 to 1977, we see a decreasing trend in temperature. This shift in climate that occurred in 77 is now known to have coincided with the shift in the phase of the Pacific Decadal Oscillation, which is an index developed by Mantua and others, and it was used to examine the relationship between Pacific climate variability and salmon production in the Pacific Northwest. You guys are probably familiar with some of you are probably familiar with these graphics of the PDO. The warm phase is represented by the positive polarity in the index and warmer than normal sea surface temperatures off the coastal Gulf of Alaska, whereas the cold phase is indicated by the negative polarity of the index and the cooler than normal sea surface temperatures off the coastal Gulf of Alaska. A number of environmental processes have been linked to the climate regime shift in 1977, and they include salmon productivity, glacial mass balances, regional drought, and stream flow patterns. Now, the study we completed in 2002 illustrates some of the differences in stream flow runoff in Southeast Alaska under the differing climate conditions. It also allows us to compare runoff during the colder period prior to 1977 to that of runoff in a warmer period after 1977. And the objectives of the study were just to identify, characterize, and explain variations in Southeast Alaska stream flow that are associated with the climate regime shift. What we did is we took the stream flow data and we divided it into two different subsets, a warm subset and a cold subset. And then we examined the differences in the annual, seasonal, and monthly mean discharges between the warm and cold periods. And for the purposes of this study, the summer discharges were taken to be the May through July average. And this represents the portion of the year when a large part of the stream flow runoff is generated from snowmelt. And the winter discharges were generated from the December through March average, when typically precip in Southeast Alaska falls as snow. Here's a map, Southeast Alaska, and the 6 different streams we used in the analysis. The largest was Mendenhall River. The second largest was the Harding River. And the Mendenhall River is about 50% glacial, while the Harding River has some glacial contribution, but it's less than 10%. The other streams were all island streams with no glacial contribution. And the basins were unimpacted by human influence, with the probably the exception of some timber harvest in Staney Creek. While the Mendenhall Valley's been developed, the gauge is on Mendenhall Lake, so it hasn't been subject to any significant development. When we looked at the annual discharges, we didn't find any significant differences with the exception of the Mendenhall River, which is what we might expect. The glacial Mendenhall River, under warmer climate conditions, increased in flow by about 10%. What was perhaps more interesting is that all the watersheds demonstrated significant differences in seasonal patterns of runoff. This slide shows the summer flow deviations from the long-term mean for Fish Creek near Ketchikan. What we did to produce this was compute the long-term summer mean, and we subtracted it from each of the annual summer means. So you can see the deviation from the long-term average. And the average summer flow for Fish Creek is about 12.5 cubic meters per second. So you can see that these deviations are actually a fairly significant portion of the average flow. This next figure shows the mean monthly flow differences between the long-term mean and the different modes of the PDO. And the warmer mode is depicted by the red bars, while the cooler mode is projected by the blue bars. We basically concluded that these flow differences were a result of increased rainfall in the winter with respect to what was snowfall in the during the colder periods. And you can see that the pattern is pretty consistent among all 6 drainages, with the exception of the Mendenhall River, which increased during every month. But the general pattern is an increase in wintertime flow since 1977 and a decrease in the summertime flow. Here's a hydrographic depiction of basically the same data, showing runoff conditions under warm conditions as opposed to the cold conditions. And once again, you can see the differences are actually quite large. The January flows are over twice what they were during the cold conditions, whereas the May and June flows have been reduced by nearly half. And this slide depicts the timing of annual runoff. And this is Cadishan River, the same as the hydrograph I just showed. And in this stream, under the warm conditions, 50% of the annual runoff is achieved by February. But under the cooler conditions, 50% of the average annual runoff wasn't achieved until sometime in early May. When we come up with a similar plot for the Mendenhall River, we see that the timing hasn't changed much in the glacial system. But what we can see on this plot is that almost 80% of the discharge for the glacial stream falls under a 4-month period from June to August, or from June to September. So the conclusions from our study were that streams in southeast Alaska have shown little change in annual discharge, with the exception of the glacially influenced Mendenhall River. Although we have seen large and statistically significant changes in seasonal and monthly discharge patterns for all the streams. Changes in the non-glacial streams were primarily a result of temperature differences altering the phase of wintertime precipitation delivery. And another important thing to point out is that the standard deviation of annual stream flow increased during the warmer period from 1977 to 1998, suggesting that the variability of flow might be increased under warming climate conditions. So the study results that we came up with are fairly consistent with climate model projections. We have reduced snowpack in areas of marginal snow cover, and it did result in a change in runoff timing. The glacially influenced streams demonstrated increased runoff and variability in annual stream flow increased under warmer conditions. Increased precipitation, that was a little more questionable. There were some increases in Juneau and Sitka when we look back at the precip gauges, but the increases were small, they weren't statistically significant, and they weren't apparent in the regional runoff for southeast Alaska. So how does this relate to this forum? I guess the potential impacts of climate change on runoff and hydropower are probably going to depend primarily on the source of your runoff. If you're concerned, if the hydropower sources for Juneau have a glacial source, some of the things we're going to want to be concerned about are the size of the glacier and the rate of melt. For instance, in the case of a small glacier that's been receding since perhaps like the Little Ice Age, if we've been gauging that stream and determining that the average discharge is 100 CFS, but we're losing mass to the glacier, we're essentially mining that water. And we might have a disappearing source of hydropower. So if the worst case scenario would be if most of our water was sourced from perhaps a collection of smaller glaciers that are all receding, in which case we could see a gradual decline in the runoff. If we're interested in non-glacial runoff, it's probably not going to be much of an issue if reservoirs are able to store the flow. While the patterns of runoff might change, the differences in annual runoff probably, barring a change in precip, will probably remain fairly stable. Some of the things you might look at if you were concerned about the changing patterns of runoff would be the drainage elevation, the proximity to the coast, the existence of seasonal snow fields, and perhaps some other basin characteristics. In general, there doesn't appear to be much of a problem with reduced runoff due to global warming in Southeast Alaska. Probably some of the more significant implications would be to like the local ecology. If you're a salmon or if you're a seal or something like that, then these changes in runoff patterns might have some more profound implications than they do for hydropower generation. And that's about all I have if you have any questions.
So we have about 10 minutes, and again, I ask that you wait until you get the microphone to ask your question.
Any estimates on the proportion of flow from glacial watersheds that is from net loss in storage or ice melting that would allow you to extrapolate to the future for a non-glacial situation for what annual runoff would be?
One more time with that question?
Okay, when the glaciers go away, that increase in annual flow from melting ice will go away, but the drainage area will not. So they'll be receiving the same precipitation they ever did, or maybe a little more. So any idea on what percentage of the present annual discharge is net loss in storage?
Oh, for say like the Mendenhall River.
Yeah.
I think Roman Matika came up with an estimate, and I want to say it was around 10 or 12% of the annual discharge was net loss in storage for the Mendenhall. And that was based on probably not a long-term data set, but probably like the last several years.
But the predictions are also that rainfall, or some of the predictions, is going to increase slightly, maybe because of wetter summers or whatever. So we may end up with no net change.
Yeah, that's a possibility. Increased precip and increased temperatures, they could kind of cancel. We kind of played with that too, because they could kind of cancel each other out. We saw increased precip at Sitka and Juneau, but we didn't see any significant increases in runoff. So we thought, well, maybe ET increased. So conceivably, you could get increases in precip and actually not see increases in runoff.
Thank you. A couple points of comment and then a question. I remember the winter of 1977 because I lived in a small community where it never got above freezing for almost 90 days. And when you're on crutches, you remember those things. And this is down in Colorado, so actually Mr. McLeod is familiar with Alamosa, I believe. Are you aware of the study, or are you privy to any of the information that they're taking from the Mendenhall Glacier regarding whether or not it's growing in size with the increased precipitation?
The last I heard, Mendenhall Glacier is shrinking.
It's shrinking, okay. And with the 77 step change, would that single fact, wouldn't that sort of go against a global warming as a cyclical fluctuation if it's that much of a step? And have you been able to point to anything to specifically attribute that step to? Have you been able to pinpoint a cause?
Yeah, no. And how does that relate to global warming? I don't know. Perhaps warming occurs as a series of steps rather than a gradual trend.
Thank you.
Ed, can you comment on, and this might be beyond not specific to this study, but to what extent USGS or other agencies are monitoring stream temperature in our anadromous streams in Southeast?
Not much.
That's scary.
Of the 6 streams I showed here, 2 of them have been discontinued since, we had a fairly limited number of streams we could look at from a long-term perspective, and 2 of them have been discontinued since we completed the study.
Funding constraints?
Correct.
You mentioned the thought, discussed a little bit, potential effects on hydropower, and if you've got adequate storage, perhaps given that annually the volume is similar, that hydropower projects probably could continue kind of like they are, I guess, or something like that, or it wouldn't change the total output that you could come up with. In Southeast Alaska, a lot of our hydropowers are smaller, either run-of-river or something like that, where they've got just a small diversion that fills a pipe. There is no storage, and they take 10 CFS or 20 or however big the system will allow, and there is really no storage. As I interpret the graph that you showed there, it looks like the shift will be for more even flow throughout the year, with where it used to be frozen up in the wintertime and not a lot of runoff. That will be increased, which that's also the highest need for energy and potentially of use there to the hydropower and to the communities that need more energy. Summertime, typically we use less energy, and the stream volume will be reducing. It looks to me like that will also be compatible even if you don't have storage. Am I interpreting correctly?
So I guess what you're saying is it looks like if you have a run-of-the-river hydropower system, the shift or the trend has been towards increased discharges in the wintertime, which is when you need the power. So it's a good thing.
It sounds like it.
Yeah,
I mean, I guess we'll
that's
see.
what I would think.
Yeah, I guess I'd want to have this discussion with some hydropower folks, and we're constantly doing that. But that does seem like potentially very compatible. And even if it's not run a river, if it's a diversion for a set amount, it just seems like you're going to have fewer times in the winter when you're not going to be able to take as much as you want. If your license, for example, says you can only take 15 CFS, and sometimes in the winter you don't have, because you have to leave 10 CFS in the stream for the fish.
Correct.
There'll be fewer times when you'll have to ramp down. You can take your full 15 for a longer period of the time. It seems like it'll be very compatible.
Right. So if there's in-stream flow reservations and issues with those flow reservations, in general, what we've seen is increasing winter flows.
There's a possibility there could be some issues in the summer then.
Yeah, there are.
Ed, I wanted to just comment a little bit on the PDO, and it seems to me that in the even in a context of climate change, we could still switch back to a cold PDO.
Sure.
And so, in that respect, and that could be for decades. And so that type of a switch could have a much larger local impact on stream flow than the long-term trend of global warming.
Yeah, almost certainly. I mean, you saw those graphs are pretty, for when you're looking at seasonal stream flow patterns, it makes a pretty big difference.
So this might be a good moment to invite our two previous speakers and the participants in the roundtable to the front. So be thinking of your questions for all of them and give us 30 seconds to just get organized at the front here.